This is going to be a super short video today. Nothing too complicated, just a real basic review of two very specific types of functions. And basically what their graphs look like so that you can, refer back and understand behaviors. So by definition, a polynomial function is the sum or difference, these could be subtraction as well, of power functions, so x to a power, with a coefficient, so a sub n minus 1, a2, a1, a0. Those are just numbers. Those are just coefficients. All right. So if you have subtraction, that's probably because the coefficient is just a negative number. All right. But what's really important to note is that n, the exponent, has to be a non-negative integer. So it has to be an integer, countable number, and it has to be non-negative. So it could be 0. And I'll give you an example of where you would have n is 0. In the last term here, you technically have x to the 0th power, but x to the 0th power is just 1. Okay, so you don't technically need to write x to the 0th. But polynomial functions are those that you deal with first after linear functions in algebra class, so this isn't anything new for you. All right, so here are 3 examples of some polynomial functions, real basic. All right, you've got f of x is x squared, that's an integer, 2. Plus 3, that's a coefficient, that's one of your a sub n's, right, or a sub i's rather. X to the first, that's an integer, and then minus 5, and technically you have the x to the 0th here. So I'm just going to go in and put those in there. Not that we need them, but just so you can see that you have integers 2, 1, and 0. Okay. Most of you would recognize this as a quadratic function whose graph is a parabola. Okay, so when I say what kind of function is this, the answer is not parabola. It is quadratic. Its graph is a parabola. Okay. All right, over here, g of x, it's written in a different order, right? Normally we like to write things in descending order from highest power to lowest, but we can sometimes write them in different ways. So g of x is actually a linear function. So its graph is a line. But you'll notice that the constant term here is 2 is actually my leading term. That's my x to the 0th term minus x to the first. And the reason it's written in this order is it's just a little bit more pleasing to the eye to see 2 minus x instead of negative x plus 2. Okay. And then we have h of x. All right. And this is a 4th degree polynomial. All right. And its graph doesn't technically have a name, but I'll go ahead and give you guys a few examples of what these polynomials might look like. All right, so you have your x to the 4th term. You have a 3 coefficient, x cubed. This is 2x to the first, so minus 2x to the first. You'll notice that you have no x squared terms, which is okay. And then you don't have any x to the 0th terms either. Again, that's totally fine. Right? You don't need to have every term of every degree in a polynomial present there. Okay, so just a few graphs of examples of polynomial functions. The first one I would do would be, a constant function, meaning if your n is 0, right? If n is 0, then you have an a to the 0, which is a constant, and a constant function is graphed as a horizontal line. Okay. Then we could go to linear functions, right? And the parent linear function, I'm going to draw the parent functions. Okay. The parent linear function is y equals x. Okay. But I'm just going to label this linear function. All right. The parent quadratic function would be y equals x squared, right? So that graph would just be a nice, easy parabola. And so we're going to call this a quadratic function. All right, this is the graph of a quadratic function. All right, I'm going to go up one more and then I'll stop because you'll start to get the idea of what happens here. So I'll do a cubic. All right, so a cubic function will be a little steeper. And if you cube negatives, you can get other negatives. So this would be a cubic function. Now you can use the textbook and go back into the appendix for some algebra review to see more versions of polynomial function graphs. But what I'm trying to tackle here is getting you to remember that all of these are smooth and continuous for all x in the real numbers. It's very important because what that means is that I can take the derivative of a polynomial function at any value for x. Okay, and we'll be using that as we go through the next unit. All right, so that's your basic definition of polynomial functions. Let's go to exponential functions. And so I wanted to stick to just the parent exponential function, and parent meaning it's the basis function. It's where, we begin. All right, and then we can perform some transformations, which we'll do on the next page. Okay, so for a parent exponential function, right, we have basically a number, a. It has to be a non-negative number. It actually has to be strictly positive, so it can't even be 0. And it can't be equal to 1 because 1 to any power is 1, and then that just becomes a constant. So a can be any number greater than 0, but not 1. So the difference here is we're raising variable powers to constant exponents, variable to constant for polynomial. Reverse that, and now we're writing constants to variable powers for exponential functions. All right, and so exponential functions in the parent form will have one of these these are just 4 examples here. 2 to the x, a number to a variable power. 3 to the x, that's a number to a variable power, a number to a variable power, a number to a variable power, and so on. Okay, and the parent function graph will have a horizontal asymptote, which we've been drawing these. We've been sketching these in class and in the review videos, but just wanted to go over it again. It's got a horizontal asymptote at y equals 0 because you can never get a negative result from this, and you can never get 0. All right, so it might be important to go ahead and say, hey, you know what? No matter what I do, this thing is always going to be positive. All right, but as you raise a number to negative values, you're actually making it smaller, right? Because you're flipping it. You're taking the reciprocal of that number to whatever power you're dealing with. All right, but at x equals 0, anything to the 0th power, if you remember, is 1. So we know that we have a coordinate point on this graph, 0, 1. All right, and we know that exponential functions are increasing functions. So this is the general behavior of an exponential function. All right, and what we'll do next, all right, is we will take a look at some transformations of exponential functions, which are still considered exponential. Okay, so as long as we see the parent function's graph, we understand that this one, as well as the polynomial functions, is smooth and continuous for all x. In other words, I can plot a point on the graph of this function at any value for x. Okay, so how did I write it before? All smooth and continuous for all real numbers. So for all x in the real numbers. Again, meaning we can, sorry about that, we can differentiate an exponential function at any real number. All right, so we're going to go ahead and look at some transformations of exponential functions. So these are just examples of slightly more complicated exponential functions. So f of x equals 3 to the negative x. I'm actually going to go ahead and graph that with its parent function first. Okay, so don't forget, we need that horizontal asymptote of y equals 0. And we know that if we plug 0 in, we get the point 0, 1. Now, if I were to graph 3 to the x, not 3 to the negative x, okay, 3 to the x would look like this, and I'm just trying to lightly do it for myself. Right, because by definition of the exponential function, that's the shape we should have. Okay. Now I can plot another point there. Okay. If I plug in 1 for x and 3 to the x, 3 to the first power would be 3. Okay, so I'm just lightly graphing that for my own reference. Let's now figure out what 3 to the negative x looks like. So this is a transformation that is a reflection over the y-axis. And the reason for that is because every x we had before, we now need the negative of it. So these positive x values will become negative, but give me the same y's. And negative x values, the negative of a negative becomes positive, but give me the same y's. All right, and so I'm just going to try to draw this as a reflection over here, best I can. All right, so oops, it's a reflection over the y-axis. All right, so you're going to have the point, 0, 1. I'm just going to go over that in purple because that's what I'm graphing. But then instead of the point 1, 3, 3 to the negative first is 1/3. So 1 1/3. Oops, made a mistake there. Sorry. 1 1/3. I have plotted it in the wrong spot. My fault. Excuse me. Having a moment. 1 1/3. Sorry, we're still at x equals 1. And if I want to reflect this over the y-axis, this becomes not positive 1, but negative 1, comma 3. Sorry about that. Okay. Now, negative e to the x. Let's look at this one next. So again, let's graph the parent function for e to the x, and then we'll use transformations to figure out what negative e to the x looks like. So again, let's get our horizontal asymptote in there, right? And as always, our coordinate 0, 1, and our general behavior of the exponential function. All right, and this is me looking at e to the x, y equals e to the x. So now, instead of the point 1, 3, I'm going to have 1 e to the first, which is just e. And I want you to remember that e is a number between 2 and 3. It's 2.7 and change, okay? So when you're graphing things with e involved, you've got to remember that your placement for e will be very important. Somewhere between 2 and 3 is sufficient. Okay. Now, the negative in front of e to the x means that all of the y values I got from e to the x will now be negative. So instead of 0, 1, I will be down at 0, negative 1. I probably shouldn't put that there. I'm going to move it over to the other side. And instead of 1e, I need to be down at 1, negative e. And so our reflection over the x-axis will look like this. Also exponential function, just a transformation of it. Okay. Lastly, let's look at this guy. And then I want to remind you, you're not limited to these scenarios. Again, we're going to go ahead and put our horizontal asymptote in. And let's start with 2 to the x instead of 2 to the x plus 1. So again, we would start with 0, 1. All right, and we'd have our increasing exponential function, that basic behavior, which means we'd have a coordinate here at 1, and then 2 to the first is 2. And I'm hoping you're seeing a theme here. Now, if you add one inside the function, that means you shift it to the left 1 unit. So shifting this to the left means instead of being at 1, 0, we will, or sorry, 0, 1, we will be at negative 1, 1. Okay, I'm gonna move that one as well. I don't like where I put it. So instead of at 0, 1, we're gonna be at negative 1, 1 because we moved to the left 1 unit. Instead of being at 1, 2, we will be at 0, 2, again, shifting to the left 1 unit. And so then basically we just shift our graph over 1 unit. And we have y equals 2 to the x plus 1. All right, so again, exponential functions can be transformed, they can be moved, translated graphically, right? So any of these would qualify as exponential functions.